Yeah, so this community, the Ocean Worlds community and the Coastal Command of the Royal Air Force in World War II actually have a sort of common interest, which is finding small, interesting things in big oceans. And this is a rearward-facing camera view from, I think, a Canadian Liberator bomber looking at a couple of depth charge explosions in proximity to U-564, I think. So what this talk really aims to do is look at the question of evaluating scientific value and the expectation of that value. So if you need to rush out and catch a plane, this is the bottom line, that I think we should be attempting to define carefully success metrics for what we do. This isn't something that comes especially naturally. The claimed metric for mission prioritization in the previous decadal survey was science value per dollar. And there is a very well-established bimodal methodology for assessing mission cost. You can do bottom-up estimates, figure out, how many boxes of X, Y, or Z you need, and it's, so many dollars per box and so many labor hours to lay out a drawing and whatever, you add it all up. There are also top-down parametric models where you say, oh, this is a radar, it's a radar that takes 100 watts, and 100-watt radars are usually, 50 million or whatever it is. These models are all wrong, right? Missions always seem to overrun, but at least there's an established methodology, and it's quasi-scientific. But it seems that the science value is assessed in these exercises by having a committee of scientists in a room and getting crayons out and coloring in a spreadsheet with red, yellow, and green as to how effectively various science objectives are met. And I can't help thinking we can do better than that. So this is sort of a work in progress. Some of that progress is articulated in a couple of papers that are out imminently. So I take some inspiration from what's called operational research or operations research, which was developed in World War II. And this is basically just taking a relatively rudimentary statistical approach to evaluating mission success. And it's more a sociologic problem than it is a mathematical one. A lot of the mathematical aspects are quite simple geometry, right? If your depth charges have a lethal radius like this, then what is the optimum spacing to maximize your chance with 3 depth charges of catching that German U-boat? The math is pretty simple. The trick is the sociology of asking the right questions, not just running off and getting in a plane and chasing subs. It's just asking what is the right way to do this to maximize our return. And the photograph at the beginning is a type example, right? You can't do this math problem without knowing how accurately the pilot is likely to place that stick of depth charges. And so the statisticians went to the Air Force guys and they said, so how accurately do you think you can place that stick of depth charges? And squadron leader or whatever says, oh, 50 feet. Our lads can do it 50 feet. And the statisticians were like, really? I mean, even in training, when nobody's shooting at you and the lighting's good, you only get 80 feet. You won't mind if we put these cameras on this plane, will you, just to get a bit of data? And after a summer of data, they got these 13 data points. This is the flight direction and the middle of the stick. And what they found, even with this rather austere data set, is that when you take the mean of these blast points, they're aimed rather ahead of the U-boat. Basically, the pilots were instructed to kind of lead, aim a bit ahead of the U-boat so that, by the time they got there, the depth charges would fall in the right place. But distances are difficult to estimate on the flat sea, and it turned out they were basically overdoing this correction. So the simple result of this exercise was, okay, don't try and correct, just aim straight for the conning tower. And that moves this point, this distribution a bit closer, and resulted in probably 2 or 3 additional sinkings per year. Each submarine sunk probably was prevented several tens of thousands of tons of shipping from being sunk. Every little helps, and in fact, the efficiency of submarine hunting went up from like a few percent at the beginning of the war to tens of percent per sortie. Anyway, the point is, taking a step back and thinking what are we doing, and trying to measure how well we do it, can yield benefits. And in an environment like World War II, Great Britain, where resources were tight, resources are also tight in planetary exploration. To maximize our scientific return, maybe we should have a think about what it is we're actually achieving. So in open-ended exploration missions, that's actually very hard to do, of course. You basically assemble a portfolio of instruments to address a range of scientific questions, and more instruments are better. Having multiple instruments together on the same platform gives you some synergies. There's kind of 1 plus delta exponent probably. Nobody's really done this in terms of assessing number of scientific papers written, because that kind of comes down to how much money you give the scientists. The scientists will write papers however bad the data are. But more data is better. Probably information value goes as something like the logarithm of information of data volume. As you see more and more patterns emerging, as you access smaller and smaller scales of phenomena. So this is hard, but it's easy to at least express at this level. When there is a single question, and a lot of ocean worlds exploration has been motivated by this single question here, it's possible to develop a rather formal information metric, which basically is the logarithm of the odds ratio. How likely is the answer to be yes versus how likely is it to be no? And a simple historical precedent is life on Mars, actually. The lead investigator of one of the Viking experiments expressed the opinion that, it's 50-50, right? You don't know any better, so it's 50-50. Until the results of the labeled release experiment and the gas mass spectrometer came in, and then he changed his opinion to be about 2%. And you can take the odds ratios going from 1 to 1 to 49, and you can express it in bits if you like base 2. There's actually a World War II code-breaking metric called a ban or a deciband, and so basically the object of the exercise is to shift the needle one way or another. You actually get more information value if you completely overturn the previously accepted wisdom, right? If everyone thinks that Europa is dead, and you find that actually there's very strong evidence for life, that's a bigger information gain than everyone assuming 50-50. So it is important to take priors into account. Similarly, if everyone's pretty sure that Europa has an ocean, and this was actually the original motivation for the Europa flagship studies that eventually evolved into Clipper, was to demonstrate that there was an ocean. But by the time we got to Clipper, kind of everyone accepts that it's there, which is an interesting dynamic that probably a historian should explore. You probably don't get a lot better in terms of if you use a community vote as a proxy for scientific certainty. If you look in the literature on global warming, there is a dissenting opinion of the order of a fraction of a percent. So maybe even with relatively incontrovertible evidence, you're not going to persuade everyone. But it's a start. So there's some lessons to be learned from the Mars organics history more generally, that there were traces detected by the GCMS, even though the general result is that Mars was organic free. This may actually have been a result of the soil oxidants. And of course, the Phoenix mission actually discovered some oxidants, the perchlorate specifically. And there's been some of the literature with Navarro Gonzalez and Melissa Guzman suggesting that the Viking data, which they've rescanned actually from the original microfiche, are consistent with perchlorates destroying organics that might have been present. The original investigator, Klaus Biemann, before he passed away a few years ago, stood by their original interpretation, which is that the chlorinated organics were actually a cleaning contamination. But the point is, this whole story is really about the qualitative disagreement of the explanation for an observed signature, i.e. that it's a contamination issue, rather than, it's nothing to do with detection limits per se, it's more, is this the result of something we haven't thought of? And this, you can contrast this with the Curiosity rover, which has taken dozens of samples in different places, really the organics detection in the mudstones that it made have been really not contested as far as I know. This is considered a pretty robust result. So, what's the difference between these? One is number of samples, one is the change of context, right? You can, with a rover, you can look in places where you know there's no signature, and that helps you establish the blank levels, the background. Anyway, there's a multiplier to the expected scientific value, which is that the expected scientific value implicitly assumes you can land and get to the site and get the sample into your instrument. And the historical record on the success of achieving those steps is actually quite dismal. Launch used to be a very risky business. The modern launch vehicles actually now have very, very high reliability rates. Adopting a new launch vehicle is still a risky proposition. Out of N trials, your expectation value, if there have been K successes so far, is given by this expression. So if you're trying a new rocket for the first time, you should have 50-50 chance of success. So if Europa Lander or whatever is the third SLS, beware. Landing, even with the recent successes at Mars, is something like a 60-70% proposition. Both Curiosity and Schiaparelli qualitatively flew with guidance software errors. Both had bad code. Now, Curiosity ended up landing 3 sigma slow because they had a wrong gravity number in the code, and Schiaparelli cratered into the ground because they corrected for a radar altimetry error wrong. But you can argue that those, that could have gone the other way. So despite all the reviews and the paperwork, the overall historical record isn't great for digging dirt and getting it into instruments, or even of landing. So that may influence whether a prudent architecture has a single landing vehicle, or, as in the earlier days of planetary exploration, including Viking, whether you have 2 landers. You multiply the science value to some extent, but you also defend against terrain hazards and other risks. There's another lesson also from the 70s, which is the discovery of the benthic microfauna at seafloor hydrothermal vents. And I think the popular narrative sort of has Bob Ballard parachuting out from the sky in Alvin, and ta-da, there's a black smoker with tube worms and all that. And that's true, but it's only part of the story. The reality is there's a huge scale change here, and this is Chris's bread and butter, right? This sort of circle is Europa-sized, and out of all this ocean, there's this sort of little spot here, which is even a little box in here. You go from the thousands of kilometer scales of ocean down to little oases that are just a few tens of meters across, and there are only a few of those. So even if you have the targeting information to say this is the right part of the ocean to go to, picking a random spot in here, you only have a fraction of a % chance of landing in the right spot. And the reason that they did go to the right spot was that there was reconnaissance at an intermediate scale. That in fact there were tens of kilometers of traverse with a towed sled, a few tens of meters above the seabed, taking a flash photo every 5 seconds. There were temperature and other data to indicate the presence of hydrothermal plumes. And these data increase the a priori probability that a not very abundant biosignature might be present in these particular spots. And I think the same consideration will apply to Europa or other ocean worlds, right? If this is Rhadamanthus linea, and there's sort of these dark patches that are not unreasonably interpreted as some sort of spray of ocean material. So that might be good stuff to look for if you're interested in what's in the ocean. But you can see there's like a little bright notch here, and maybe that's where the spray has been shadowed by a rock on the crest of the ridge or something. It doesn't matter. There are geological processes that yield heterogeneity at all scales. So, how well can you be sure that you're going to not land at a dry spot? That's an important question. And it's well known in Mars exploration and has been articulated for decades, and we're seeing the benefits of it now, that mobility brings important advances. And it's worth just articulating in a quasi-quantitative way what those advantages are. And the first thing is that interesting places tend not to be the places you want to land. The places with high landing success probability are typically not the places that have the interesting biosignatures in a detectable place. So if you have the ability to move around on the surface, you can break that coupling, right? You can land at the safe places and then transit to the interesting ones. If the probability of detection per site is small, then going to n sites multiplies that by n. Okay, as PD gets large, that there's another statistical expression. But to a first order for low PD, it's the multiplier. You can evaluate the present likelihood of biosignature presence at a much finer scale with the data that you get once you're closer to the target. That's important. And then there's the issue of deliberately sampling low probability materials. Curiosity was able to ingest some sand that is just basalt. It's nice and clean, and actually it abrades the surfaces of the sampling system and essentially performs an in situ cleaning. So mobility brings all these advantages, and so it's not for me to say whether a given architecture is worth doing or not, or a given number of dollars. I'm just trying to outline some tools by which the information value can, and I'd argue should, be assessed for a life detection or planetary science mission. I'll underscore that the priors are important, how much you think you know ahead of time. And that there are various factors that always enhance a mission. Reconnaissance data that I guess Clipper will give us for Europa, mobility, and the ability to assess the false detection rate in situ and have enough time to resolve anomalies with ground in the loop. So hopefully that gives you some food for thought as you head back to your respective institutions. So thank you.
So I had a question, and I want to stress that we said this was a judgment-free zone on some of these questions. Why was the a priori assumption about life on Mars 50-50, and I know that wasn't your mark, that was just what he said about it, and on Europa, because any world that we have visited that has an ocean, which is one, that we've been able to probe, has life, and then and the same for Mars, right? I mean, obviously you wouldn't say it was 1%, there's nothing there, or 99% that it will be there, but it seems that it should have, the probability that Mars had life and that Europa could potentially have life should have been much higher in our initial assumption.
Really? I think the straight answer to your question is if you either don't know anything or you don't know how much you don't know, then 50-50 is the most agnostic guess that you can come up with, right? If n is 0 and k is 0, your expectation probability for anything is 50-50. Now you can introduce whatever prior information you have, which is that there are oceans, or that the origin of life requires tides or hydrothermal vents, or whatever precursor information you have. But in the absence of any of that, you say, well, 50-50. I guess actually we have k equals 1, n equals 1 for the Earth, in which case your prior should be 66%. But it's more a philosophical than an algebraic question.
I think that's an interesting way to quantify the value of new information. Is what you were just discussing, and it makes me think about how often in the news we've seen they discovered water on Mars or something like that. But so it makes me think maybe we shouldn't really stick to a strict quantitative approach for the value of new information, because there's so many different ways to test hypotheses in new ways, and to look at information from a different instrument or a different angle to reconfirm. And there's a lot of value in testing previous work.
Yeah, so the sentiment which I think you're expressing, which I've heard before in some of the referees' reports on these papers, is this is hard, maybe we shouldn't try, and I'd contest that. Yeah, I mean, yeah, I mean, I think, and I don't claim to know the right answer for how to do this. But I think some sort of framework like this is a more rational, defensible, and transparent approach than at least the crayons in the smoke-filled room. But as I say, this is a work in progress. I want to start the discussion, and you're right. The framework of previous work, previous hypotheses is a very important starting point.
So, are you suggesting that this something could be used for instrument selection or mission selection, or is it something that's only useful after the fact in assessing?
That would be a very rational application of such a methodology. I'm aware that any time you define a metric, people will find ways to game the metric, and scientists are kind of smart people, and they will devote effort to that. Yes, in principle, it should be a guide to selection among mission architectures, instrument suites. Sure. Fine by me. I've got all day.
This is a really cool approach. So the decadal recommended it as science per dollar, and you were talking about ways to quantify science return and include risk. But seems like swapping out one trade for another. You have cost, risk, science return, programmatic timeline, and things. And so, would an end goal be that you're able to use the full trade space in down selection and apply that sort of the science return, or why specifically is risk coming into play for science return, but not the other trades?
So yeah, that touches on a question that I talked about a little bit in an article in Aerospace America last year called "Engineers Are Dogs, Scientists Are Cats." Mission design is typically an optimization process, but scientists and engineers view that optimization in a very different way. The scientists tend to go to an engineer and say, "What is the most science you can give me?" Subject to whatever physical constraint it is, the size of a rocket or the throw weight or whatever it is. The engineers tend to look at it as a constrained minimization, which is, what is the smallest science you will accept? And that dynamic tension is what kind of gives us the missions we have. And you get the best results when the scientists kind of understand what the engineers are trying to do, and vice versa. So what is the cost function we're trying to optimize? I mean, if you're looking at mission architecture, you get a different answer for what is the maximum possible science per dollar, which might be a single lander that has, it might get lucky, it might discover life, but that's the investment strategy that people apply when they buy lottery tickets, right? It is a rational answer to the maximum possible value one can get from the dollars you have. Or you could put the money in the bank and be absolutely sure, you have a high certainty of getting a smaller incremental return. So, this is a wider discussion, and I don't claim to know what the right answer is, but I'm glad you're thinking about it.
I just had a question. Oh, sorry, somebody else. Okay. About how we value discovery or like finding out things that we had no expectations or prior knowledge, or if you had a mission concept to go, I don't know, just explore somewhere that you maybe something's going on but you don't know. Like, how can you give a value to that in some way, or?
Well, almost by definition, no. I've spent a number of years now doing discovery and other proposals, and I have to despise the construct called a science traceability matrix, because it essentially attempts to break down scientific discovery into this box checking exercise. And while it does have a sort of formality to it, it doesn't really do exploratory science many favors. Yeah. So the two answers are one, this one. Whereas if you don't know what you're going to find, then maximizing the number of ways of finding new things, the different sensing modalities and the resolution or duration or coverage or whatever the data metrics are. Maximizing those maximize your chances of discovering something. The other aspect is what's known already, right? If you're going to going to the Uranus system, for example, there isn't so much data, right? There's a lot of low-hanging fruit once you get there, right? Even just a few new pictures of the Uranian moons will tell us a lot more about how those worlds evolved. Whereas if you took the same data in the Jovian system, where there have been several missions already, then you don't learn so much. So this how much is known already is a critical part of that calculation. But that's all I can offer for now.
Well, then I'm going to add something. I've been waiting to ask you this all workshop long, maybe a couple of slides forward. How does Oliver Cromwell fit in with the search for the life on Europa?
Thank you so much. So this is if you Google it, you'll find this story. So what it is a statement that the probability of anything is never 0 and never 1. Right? You're never absolutely sure of anything. A coin toss might land on its edge, eventually. So the quote basically is one from a letter from Oliver Cromwell to the Church of Scotland in 1643. And I can't remember the reason for this, but the quote is, by the bowels of Christ, consider you might be mistaken. Basically it's an appeal to the fact that, think about the possibility you might not know everything. So that's where it comes from. Because what it means is that you cannot be sure of anticipating the results. You cannot be absolutely sure that your mission is going to land where you think it's going to land. And as soon as you step away from that certainty and start thinking about, start putting a number to a probability, then you make a lot more progress. It works the other way too with planetary environments. There's all these kind of voodoo bogeyman, what if a giant chasm opens up underneath the lander? What if there is a dust storm when you're landing? Whatever it is. When you articulate those hazards as qualitative possibilities, then you can't do anything. You stay home because space is frightening. But if you say, no, the probability of a dust storm in this season is 0.5%, then you can rationally assess that against the other risks, like launch, and say, okay, this is a risk. We accept this risk and we'll go ahead, knowing that. But as soon as you start thinking about it quantitatively, you can do things in a rational way. If they're 100% or 0%, they're qualitative, and there's no argument about